Jai Hind. So today we will discuss the subject theory of automata and formal language. Subject code is KCS 402. So it is very important subject as AKTU point of view and many university exam point of view and many competitive exam. And today's topic is push down automata. Very important topic. In short, we call push down automata as PDA. Okay, so let's start. So let's understand what is push down automata. Okay, so in order to accept the regular language, we need finite automata. Okay, so to accept the regular language, we require finite automata, but when language is CFL, context free language, then it is not possible for finite automata to accept the language CFL. So to accept the CFL, we require one more machine. It is almost similar to finite automata. Okay, and we require that machine. That machine is PDA. Okay, PDA is almost similar to a finite automata, but there is one difference, that PDA is equivalent to finite automata plus one memory element is added. One memory element is added in finite automata, that is one stack. One stack is added and that finite machine or finite automata will become the PDA. So let's say in order to accept the CFL context free language, in order to accept the CFL context free language, we need a machine which is similar to finite automata. Okay, it is similar to finite automata. Push down automata is a finite automata with extra memory. Push down automata is finite automata with extra memory, and that extra memory is the stack. Okay, we know that on stack we perform push and pop operation. Okay, so in finite automata, if we add stack, then it will become PDA, and that helps push down automata to recognize the CFL, context free language. Okay, push down automata recognize the CFL language. Okay, so let's see the graphical representation of PDA. So there is input tape, here we give the input, and there is finite control, and this finite control is connected with memory element, that is stack. Okay, this is stack, that memory element is stack. Okay, on stack we perform two operations. One is push operation, when we insert the element into the stack, and pop operation, when we pop out some element from the stack. Okay, there is one reading head, this head only reads the input symbol. Okay, it will not able to write, and it moves only in one direction. It moves only in one direction. Okay, it is only a reading head and it moves only in one direction. Based on input and PDA, this on stack, this PDA either accept the string or reject the string. Okay, either accept or reject. Okay, and here Z node is the initial bottom of the stack symbol. Okay, this is the initial stack symbol which is at the bottom of the stack. Okay, it shows that it is the bottom of the stack. Fine. So this is the basic graphical representation of push down automata. Now next see the tuples of push down automata. Tuple of PDA. A push down automata PDA can be defined as a, we define usually with M. There are 7 tuples Q, sigma, tau, Q node, Z node, delta and F. So let's see one by one. First tuple is Q. Q is the non-empty and finite set of state. Since set of state cannot be empty, at least there will be one state and there cannot be infinite state. Okay, so that's why it is non-empty and finite set of state. Second is sigma. Sigma is non-empty and finite set of input symbols. Okay, it is also non-empty. It is not possible that sigma equal to 5 or blank. This is wrong. Okay, this is not acceptable. Second is, it is not possible that sigma can have infinite number of symbols. Okay, this is also not possible. Okay, it must have non-empty and finite set of input symbol. Okay, next let's see, third symbol is tau. It is the set of push down symbols which can be pushed or popped from the stack. Okay, fourth is Q node. Q node denote the initial state in the push down automata. Next is the Z node. Z node is the initial bottom of the stack symbol. Okay, so this is Z node. This is Z node. Okay, so this Z and this Z is same. Next, delta. Delta is the transition function. Okay, here the transition function is defined as that there is one present state, there is input symbol and there is top of the stack symbol. Okay, there is some present state, input and top of the stack symbol. Then it will goes to some next state, okay, some other state, and change the top of the stack symbol. According to the required operation, it will change the top of the stack symbol. So this delta is defined as there is some state Q, that is the current state, present state, and there is input symbol sigma and epsilon, sigma union epsilon, and there is top of the stack symbol, that is tau. Then it will go to the some other state and there is some symbol, okay, on top of stack which can be written or popped or push operation, it depends. Okay, so in a given state, PDA will read input symbol and stack symbol from the top of the stack, okay, and move to the new state and change the symbol of the stack. So this is the meaning of transition function. Okay, next tuple is F. F denote the final state. There is one more important thing that is very important. Okay, this is very important. So sometime final state will be empty. It means it is not necessary that PDA must have final state. Okay, so that is we could accept the string without the final state. Okay, this is very important from PDA point of view. Okay, so next see the PDA language acceptance. PDA language acceptance. So there are two ways to accept the language by PDA. First method is language acceptance by final state. Second is language acceptance by empty stack. First is language acceptance by final state. Second is language acceptance by empty state. Okay, so let's see one example or construct one PDA to get the more and clear understanding of the PDA. So here the example one, see given that construct the PDA for the language L equal to a raised to power n, b raised to power n, and n is greater than equal to 1. Okay. So before going to construct the PDA, let's see some understand how we can do that. So there is stack, okay, there is stack, fine. For example, let's W equal to A, B, B, which is equivalent to same A raised to power n, B raised to power n. Okay, and here is the initial stack symbol. Okay, first A come, okay, then A will be push. Okay, now move forward. Now A come, top of the stack A. Now A will be push. Till now this A will be push. Okay. Now next symbol is B. Next symbol is B, and on top of stack is A. So on saying A, this B will be, this A will be popped, this A will be popped, and B will be, okay, let me just remove that. Okay, till now this A will be pushed. Okay, now when seeing 1B, this A will be popped. Okay, on seeing second B and top of the stack is A. Now top of the stack, here initially top of the stack is this A, now top of the stack is second A. Okay, now this A will also be popped. Fine. Now my stack is contain only symbol Z node, and here the symbol is epsilon, means string is over and A is over, B is over. It means number of A is equal to number of B. Okay. So let's construct the PDA for that. As usual, we draw state Q node. Q node is the initial state. So initially when input is A and top of the stack is Z node, we pop the Z node and push A Z node. Okay, initially suppose this is stack, on seeing input A, this AZ will be, this Z node will be popped off and AZ node will be pushed into the stack. Okay, Z node and A. Okay, this AZ node will be pushed. Now when input is A and top of the stack is A, then A will be popped out and A will be pushed. A will be pushed. Okay, now move on to the next state. This A keep on pushing A onto the stack. Now when A input is, now when all A are over, now input will be B. Okay, input will be B and top of the stack is A. On saying A on top of stack, when input is B, we pop the A. Now this A will be popped. Okay. Now on input B, when top of stack is A, we pop A. Okay. We keep on doing this until all A will be popped up. Okay. When all A will be popped out, then all B will be over. Okay. Now input will be epsilon and top of the stack is Z node. We keep Z node as it is and accept. Okay, accept. This is PDA. Okay, so this PDA accept the language A raised to power n, B raised to power n, and this is known as language acceptance by final state. Language acceptance by final state. Okay, this is known as language acceptance by final state. Now see the same example, construct the PDA but language acceptance by empty stack. Language acceptance by empty stack. Okay, so let's see how we construct the PDA for language acceptance by empty stack. So the language will be, here the language is A raised to power n, B raised to power n, and n is greater than equal to 1. Okay, so there is state Q node. Okay, on input A, when on input A on input A, when top of the stack is Z node, we push A Z node. First we pop out Z node, then we push A Z node. Okay, now when input is A and top of the stack is A, then we push A. Okay, now we keep on pushing A when all A will be over. Okay, now when input is B and top of the stack is A, we pop A. This epsilon show this is pop operation. This is pop operation, and these two operation are push operation. These two operation are push operation. Okay, now I am at state Q1. Okay, again this is for 1 B. Okay, now B, on input saying B, when top of stack is A, we keep on popping A. So this is also pop operation. Okay, now when A and B all are over, okay, then when input is epsilon and this Z node will also popped out, top of the stack is also Z node, we pop the Z node also. In means here Z node is there. Okay, Z node is there. Input is epsilon, we pop the Z node. This Z node is no more present here. This stack is empty. Okay, now this is pop operation. When input is epsilon. Okay, so this is language acceptance by empty stack. This is language acceptance by empty stack. Both are correct. Okay, this is language acceptance by empty stack. Okay, now see one more example to construct the PDA. So here construct the PDA over sigma equal to A comma B for the language L such that string W is such that number of A equal to number of B. Number of this NA shows that number of A in string W equal to number of B in string W. So how we construct the PDA for that? When A comes, we push A into the stack. When B comes, corresponding to 1A, we pop corresponding to 1B we pop A, and corresponding to B we pop A, and corresponding to A we pop B. Okay, what it means, suppose this is top of the stack, when A comes, okay, and A comes, okay, when B comes, this A will be popped, when A comes, this A will be pushed, when B comes, okay, suppose A, okay, A will be pushed, when B comes, 1A will be popped, this A, this A will be pushed, this B comes, this A will be popped, and there is one more B, so this A will also be popped. Okay, this shows that number of A equal to number of B. So construct the PDF for that. There is state Q node, okay, when input is A and top of the stack is Z node, we push A Z node. When input is A, top of the stack is A, we push A, or when input is B, top of the stack is Z node, we push B Z node, and when input is B, top of the stack is B, we push B and B. Okay, now when A is the input and top of the stack is B, we pop B, or when input is B, top of the stack is A, we pop A. Okay, now I am at state Q1. Now we keep on doing this, that when input is A, top of the stack is B, we pop B, and input is B, top of the stack is A, we pop A. We keep on doing this. Okay, now input is epsilon, top of the stack is Z node, we keep Z node as it is, and string will be accepted. So this is the PDF for the language where number of A is equal to number of B. Okay, thank you.